1615. Binary search trees. Again, need to know the implementation, the concept behind it, how it works, and where things will show up, but not necessarily how. You don't need to know exactly how this whole thing works. So, sets, which is what we're still doing with, are nice because it allows me to find things quickly. There are no duplicates. There isn't a structured order to everything, like an array, so I can always get through pretty quick. This basic way of getting through a set is if I were to order it in what's called a tree and do a binary search on it. Binary searches are O log of n, right? So that's pretty efficient. That is to say, 1,000 items would take, on average, 10 steps to search through. The problem with just using an array, if I wanted to search things really fast, is that adding and removing things from an array is pretty time consuming. It's O of n operation. So we're going to introduce the concept of a tree, which is sort of a version of a linked list. So a linked list is a one-dimensional data structure. That is to say, we had node 1, which points to node 2, which points. So they're all stacked out in a row. Now, this would be a singly linked list. Remember, a doubly linked list just goes and can go both ways, so I can find myself. But it's still all in one giant row. A tree is made of nodes that have references to multiple nodes called child nodes. So I've got node here. This would be my parent, and then I can have child. I can have a child. I can have a child, etc. A binary tree, binary meaning 2, means that I have at most 2 child nodes. So I've got a binary tree, kind of like a linked list. The actual tree object knows where to find the very root first node, my root node, which has space for 2 children. Okay. Binary search trees, very carefully constructed, have a very specific ordering to them. So the data values of all descendants to the left of any node are less than the data values stored in that node, and all descendants to the right of a parent node have values that are greater. However, you're going to determine if something is less than or greater than. So if you look at page 721, we're going to do a tree by names. If Juliet is my parent or root node, and then I would add Eve coming before or being less than Juliet alphabetically, it would be the left child node. And then let's say I wanted to add Romeo. That would become the R coming after J, become my right node. Let's say I then wanted to add Harry. Well, Juliet, Harry, H-I-J-K, right? So Harry is less than Juliet. So I come down to the right-hand side, and then I check Harry is greater than Eve. So greater than means I have to go to the right. So my right child node becomes Harry. Okay, let's say I then wanted to add Tom. Okay, well, Tom is greater than Juliet, which is always my starting point. So I come down here. Tom T is greater than Romeo. So Romeo, Tom becomes the right child of Romeo. And now say, lastly, I want to add Adam. Well, Adam is less than Juliet, so it comes this way. Adam is less than Eve, so it will become the left child of Eve, and I now have my tree ordered. Now if you look at page 721, figure 8, we've got a tree that's not a binary search tree, and the reason being is that I have Juliet as my root node. I've got Romeo and Adam correctly placed. However, Eve is in the wrong place. Eve is greater than Adam, so that far side should look like this. It should be Juliet, Adam, which is fine, then it should be Eve, and then it should be Harry with null child pointers for both of these with nothing in it yet. That would satisfy our rules for a tree structure. So if you look at page 723, if I had binary search tree equals a new binary search tree. Tree add Juliet, step 1. On the figure, I add my root node. Step 2, I'm going to add Tom, which is going to become the child node of Juliet. So tree add string Juliet. So I've got Juliet as my first root. Then I want to add Tom. Tom is greater, so Tom comes here. Step 3, add Dick. Dick is less than Juliet. So that's step 3. All right, then I add Harry. Harry is less than Juliet, greater than Dick, so it becomes the right child of Dick, and on the left subnode of Juliet. And then the very last thing, if I wanted to add Romeo, well, Juliet is less than Romeo, so Romeo comes onto the right side. Tom is greater than it, so it becomes the left child node of Tom. And then I still have my binary tree. So one thing to remember, unlike a linked list or an array, and like a hash table, a binary tree has no insert positions. You don't get to pick where you want to insert an element. The data structure is what is called self-organizing. That is, each element finds its own place, although there obviously is a pattern to it. This isn't position, 3 or something like that. It's just less than, greater than checks. The tricky part can be removing nodes if I want to remove data from a tree. If it has no children or anything like that, that's pretty easy. So I want to remove a node, simply modify the parent link that points to the node so that it points to the child instead. So this is if I have just one child. So if I wanted to remove Tom, I can effectively remove Tom by just pointing the Juliet right child node to Romeo, and that'll still satisfy my requirements of that being, because anything to the right side is greater. If the node removed has no children, for instance, if I wanted to remove Harry, then I just set the right child node of Dick to null, and I'm good there. The trickiest part is if there's 2 children or more on the node I want to remove. Rather than removing the node, it's easier to replace the data value with the next larger value in the tree. That placement preserves the binary search. So looking at figure 12 on page 726, if I wanted to remove that uppermost right node, then I need to pull the data in the smallest left-hand side, the furthest on the left of its right child is the data that I need to put there. If your tree is balanced, adding an element takes O(n) log n time. If it's unbalanced, that is, it's not sort of evenly distributed, it can be a lot longer. Okay. Page 727 starts the binary tree Java class. Again, don't need to worry about too much, you just need to know how to do it. Alright, tree traversal. I can print trees using a few different methods. This is 16.6. We're not going to do too much in depth of this, but if I want to get the data out in order, that is to say, greatest to smallest or smallest to least, I have to traverse my array in a certain method. Okay, so page 731. 16.6. Okay, if I wanted to print the data in sorted order, step 1 is print the left subtree. Then number 2, I print the data, that is my parent. And then number 3, I print the right subtree. And this is actually a pretty nice recursive system because I work my way down so I don't actually start quite at the middle. Okay, so if I looked at figure 10, that's the one back on page 723, and I wanted to print that in order, it should go Dick, Harry, Juliet, Romeo, Tom. So first what I need to do, print the left subtree of Juliet, that's Dick and all its descendants, then print Juliet, then print the right subtree that is Tom and all its descendants. So how do I start at Dick? Well, I print the left subtree of Dick, in which case there is none. Then I print Dick, then I print everything on the right subtree, which in that case is only Harry. So my left subtree of Juliet would get printed out as Dick, Harry. That corresponds to step 1 above right here. Then I print the node I'm looking at, Juliet, and then I print that's step 2, and then step 3. I'm going to print the right subtree in order, in which case would be Romeo, Tom, following the order of when I'm trying to print the specific subtree, print left, print node, print the right. Okay, so that'll print something in order. If I want to print the entire tree backwards, all right, in order traversal, I have in order, pre-order, and post-order. Okay, that is an in order traversal that we just discussed. I also have pre-order, which goes root, left subtree, right subtree. I have post order, which is left subtree, right subtree, and then root. Okay, they don't obviously print them in sorted order, although they are a specific order. Post-order traversal of an expression tree yields the instructions for evaluating the expression on what we consider to be a stack-based calculator, which it pushes the number on the stack, pop the top 2 numbers, apply the operator, push the result back on the stack. We're not going to do too much with that. But you do need to know in order, pre-order, and post-order traversal of a binary tree. So last, just a quick review. The story of Speck the Spider. Now, Speck the Spider was a very orderly spider. He liked to know exactly where his food was in case he wanted specific food on a specific time of day. When he woke up, he says, "I want this kind of food." He knew exactly where it was, instead of just having things willy-nilly all around his web like all other spiders usually do. So he did a binary tree on his web. So one morning he woke up and he said, "I want a fly." So he crawled down his web to the beginning of his food tree and saw that it was a ladybug all wrapped up there. He said ladybug is not what he wanted. He wants a fly. So in his mind, he wants a nice, juicy fly for breakfast. So, first step, find the ladybug. Ladybug is not what he wants. However, you do know that fly as a value is less than ladybug. We will assume that Speck does these alphabetically. Therefore, that means he has to go, he knew he had to go to the left, the left child of his root ladybug node. In which case he found, at that node, he found a beetle. Beetle is not what he wanted for breakfast. He wants a fly. However, Speck knew that beetle is less than fly. Therefore, fly has to be on the right subnode of a beetle. So, he walked to the right, found his fly, and had a delicious breakfast.